In this lesson, we're going to look at Objective 5.2, Introduction to Rate Laws. The learning objective states that we should be able to represent experimental data with consistent rate law expressions. So through these experimental methods, we can actually monitor the amounts of reactants being consumed and how much the amounts of products being produced in a reaction. That can actually help us figure out the rate of the reaction. Remember, reactants are being consumed, so they would be decreasing in concentration per se, and products would be increasing. In 5.1, we talked about rate of disappearance and rate of formation. So the rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to this thing called a power. Now, this power, most cases you would want to assume it would be the coefficient in the reaction, but that's not always the case. This power that we raise each of the reactants to is something called an order of the reaction. So this order can be positive, negative, integers, or fractions. We generally are going to be working with positive integers. Generally, this order is going to tell us how that concentration of that reactant, how it's affecting the rate. And we'll look at that in the next couple of pages, okay? So if we look at this reaction right here, this general expression, here you can see that the capital letters represent the chemical species, and then the lowercase represents the stoichiometric coefficient. So the rate law would be expressed looking like this. Now, the reason why it's the reactants, not the products, is because the reactants are always going to affect the entire reaction. Because if you don't have those reactants reacting, you aren't going to make any products. Now, you will notice that I raised both A and B to some letter, some power. So where M and N is going to represent the reaction order with respect to that reaction. Reactant, excuse me. Now, please note, this is not stoichiometric coefficient. We will get more into why it isn't always, so you'll see in the next couple of lessons, it's not always the case it will be raised to that coefficient. Now, you may be wondering why I have this letter, this lowercase k. So k is a proportionality constant in the rate law, and we call it the rate law constant. So here the value of k actually depends on the type of reaction. It actually also with temperature and the presence of a catalyst, because the faster the reaction, the larger the k value is. So we can actually compare initial rates of reaction as a method to determine the order with respect to each reactant. If we know the entire rate, like up here, we can figure out what k is. So that's generally how the problems will be laid out. You're going to be trying to figure out what M and N are. And then once you know what M and N are, you can actually solve for k using any of the trials that they use. And so you're going to see some examples for that. But don't stress too much about k. Just know that it's going to be a constant for any type of trial or any type of reaction. And it kind of just helps us make the math work. It also helps us determine if this was a fast or slow reaction. So let's talk about this M and N, what this reaction order even means. So the order of a reaction, so with respect to each reactant, this would be the power, like what we saw in that expression where we saw M and N. Those letters were with respect to that reactant. Now, if you want to find the overall order of a reaction, you would take the sum of all the powers. So in that case, from the previous page, it would be M plus N, okay? All right, so let's look at this chart right here. So we can look at evidence or experimental data to help us figure out what the order is. And again, you're going to see how these values, these orders, end up affecting the rate, okay? So there are mostly, when I say mostly, because I said we mostly work with positive integers, you can work with fractions and negatives, but you're probably not going to see it as much. We're mostly going to have 0th order, first order, or second order, and that's just going to correlate. So you can see order is letter N, so it would be that A would be considered to the power of 0, or to the power of 1, or the power of 2, respectively. So let's focus first on 0th order, okay? So you're going to assume that this is trial 1, trial 2, and trial 3, and this is going to be for all 3 columns. But let's just focus on 0th order right now. So you will notice if I have a reaction where I only have one reactant, and it's A. Here, when I change the concentration of A, so changing the concentration of A, how does it affect the rate? Here, it has no effect on rate, okay? Has no effect on the rate of the reaction. We would consider this a 0th order for that reactant. So if we only had A making whatever our products are, I'll just say A making, let's say B. Here, having only one reactant, here our rate law becomes rate equals K, A to the power of 0. Now, if we have something that's that concentration is raised to the power of 0 and it has no effect on the rate, you could also just get rid of it. So rate would just equal K. All right. All right. Now let's look at first order. So looking at first order, you can see when we changing the concentration of A, how does it affect the rate? So here, when I go from trial 1 to 2, it multiplied by 2. Here from trial 1 to 2 for the rate, it also multiplied by 2. You can also see from trial 2 to 3, it was multiplied by 2. And even for the rate, it multiplied by 2. And even what's even cooler is if I look from trial 1 to trial 3, it multiplied by 4. You'd hope the same type of effect would happen to the rate, and it also multiplied by 4. So changing the concentration of A will result in a proportional, I'll just write out the word, proportional change of the rate. So it will do exactly what it did to the rate if you affected the concentration. So here again, example, if I had A and multiplied by 3, here the rate would also multiply 3 because of that effect, okay? It's that directly proportional thing. Now again, if I had A making B again, our rate law will become rate equals K, A to the power of 1, okay? Because this A is considered first order when affecting the rate in any type of experiment. You could also just get rid of the 1 if you wanted to. That also works as well. You don't have to indicate that it's 1 if you just have one of them. Now let's look at second order, okay? So for second order, I want you to pause the video and try to figure this out yourself. It's going to be a little bit more difficult because we looked at no effects and then directly proportional effects. Here, I want you to pause the video and try to see what's happening when you go from trial 1 to trial 2 and how the rate is affected in the other one. So pause video and try this out yourself, and then click play and I'll go over the answers. All right. So assuming you pause the video and try this out yourself. So here, when we go from trial 1 to trial 2, it was multiplied by 2. And again, we're assuming trial 1, trial 2, trial 3. Here, for the rate, how that got affected was it actually took what you did from trial 1 to 2 multiplied by 2, but it actually raised it to the power of 2, so a square function. And you can even see when we go from trial 1 to trial 3, trial 1 to trial 3, we multiplied by 4. when you go from trial 1 to trial 3, it did multiply by 4, but to the power of 2. So it's taking it that square function. So here, changing concentration of A will result in the rate changing with a square function. Okay, this one is a little bit more difficult, but don't stress too much. But again, kind of just writing this out in words. If you took your concentration and multiplied by 2, here what it did to the rate is it times by 2, but then put it to a square function, okay? Or you would say, or by factor of 4. That's how you could have also written that as well. So here, essentially going back to assuming that this is one reactant A making B, our rate law would be expressed as rate equals K, A to the power of 2, indicating that second order, okay? So here we have looked at 0th, first, and second. These are mostly the 3 that you're going to be looking at, but specifically when it comes to a lot of our data, okay? Don't worry so much about what it would look like if it was a negative half or some type of fraction, okay? All right, so this next section, before we move on how to figure out rate law expressions from, any type of data, I want to talk about what the units for K would be. So on the AP test, the units and value of K are worth a lot of points. Most cases, they're worth about 3 points total. That would be getting the correct answer, sometimes significant figures, as well as the unit. So if we actually look at this first part right here, so the reaction order is going to be the sum of all orders, okay? Again, that would be if you had, again, looking at every single reactant's power and taking the sum of them. Here, the units for K will be based off this expression, 1 over molarity to the power of n minus 1 times time. So time can be seconds, minutes, hours, it doesn't matter, but you need to use this general expression when figuring out what the units are for K. So if you look at here, if your reaction order is 0, so your rate law was, let's say, rate equals K, A to the power of 0. Using this expression at the bottom, 1 divided by m, 0 minus 1 times time, here your units become molarity over time. Now, if it was first order, so this would look like this. The sum of all the powers is 1. Here, 1 divided by m, 1 minus 1 times time. This ends up becoming 1 over time for the K units. Why don't you pause the video and fill in the rest of the chart? All right, so filling in the rest of the chart, you get the units for K. Now, I do want to look at this part right here. So this, don't worry so much about the examples. Like, again, I'm just giving you just like quick examples. But here, this would be an example of a reaction order of 3, because you would take the sum of 2 plus 1 being 3. And so here, that's when I would plug in 3 minus 1 to get 2, okay? So now we're going to focus on determining rate laws from experimental data. So there's 2 ways to do it. The most common methods. The first is algebraically. So to find the powers, the order with respect to A, let's just say you're going to pick 2 trials in which the other reactant remains constant. And then it will be vice versa. If you're solving for the order with respect to B, you'll find 2 trials where A remains constant. The reason we do that is for the first one, if you're trying to find the order of A, you want the other reactant to be constant, having no effect on the rate. So you got to pick like 2 trials where the one you're investigating is changing while the other reactant remains constant, so it will have no effect on the reactant. Then you're gonna write some type of ratio to solve for the exponents like m and n. Sometimes you can label it x and y. The other way is verbally. I would definitely do this more for like a multiple choice section since you don't need to justify your answers. Now, both methods will take the same amount of time on a free response because if you use the verbal approach, you need to explain like in a paragraph format what trials were changing and how that changed. And by the time you do all of it, you might as well just do the math, okay? So let's go look at the first example, okay? So again, the biggest thing is the goal is to find two trials where your first reactant is changing and the other one is not. So if you look at this reaction, we have A plus B making C. So we had 3 trials where A changes, B changes, and how it affected the rate. Now, so our rate law expression, remember, it's going to be based off our reactants. So here, this is the general expression. So we are essentially solving for the order, that power for X and Y, okay? So let's first start off easy by looking for what trials A changes and B stays constant. So let me go over to the to the right. Let's look at where A's changing. You'll see where A's changing and B staying constant is trials 2 and 3. A changes from 0.1 to 0.2, and B stays constant, and look, our rate changes. If our rate didn't change, that would tell us that's 0th order, fun fact. So here, how I like to set this up is I like to put the trials where I'm gonna set myself up to get whole numbers. So instead of me writing trial 2 over trial 3, I'm gonna put trial 3 over trial 2 because I want whole numbers. You don't have to do this. Now what you're gonna do is you're gonna take this entire expression right here and you're going to fill in the stuff you know from that row, that trial. So if you notice, based off that data table, you will know rate, you will know the concentration value, and you will know the concentration of B. We will not know K, X, and Y. So here, using the trial data for trial 3, the rate was 1.45. I don't know K. The concentration of A in trial 3 was 0.20 power of X, and then B was 0.20 Y power. Then for trial 2, 0.72 K, 0.10 X, 0.20 Y. So what we can do now is actually cross off things that's not going to help us figure out X. You're always going to cross off X in these type of rate law problems, okay? Then I'm going to cross off this section right here because they ended up being the same thing and it's not going to help us solve for X. So what I have now is 1.45 divided by 0.72 equals 0.20x, 0.10x. So I'm actually going to rearrange this just a little bit and make it 1.45 divided by 0.72 equals 0.20 divided by 0.10 power of x. So I kind of combine those all together. So now what I can do, let's divide those values on either side. So 1.45 divided by 0.72, then we'll take 0.2 divided by 0.1. You should get 2 equals 2 to the power of x. Here, this tells me x is first order for our reactant A. Okay? So now I know the power for x from the top. It is 1, okay? All right, now let's solve for B. Now I meant to say this earlier, but this problem is essentially a 2-part problem. We determine the rate law expression, and we're actually going to solve for the value of the rate law constant using one of the trials, but we'll get there in just a second. So looking at B, let me scroll back to my table. I can see trials 1 and 2, A is staying constant and B is changing. Now let's just say there was no trials where A was staying constant. I do just want to say, since you know what X is, you can actually choose whatever trials you wanted, okay? Just you would need to find one where B is changing. So here I'm going to do trial 2 over trial 1. And now let me plug in my entire rate law expression. And actually I'm going to decrease this just a little bit. Okay, so here I have 0.72 divided by 0.18 equals, both have K's, the A value, and now I have the B value. If you wanted to just still leave it as X, that's totally fine as well. All right, now I'm going to cross off the things I don't need. And now what I have left is 0.72 divided by 0.18. And I'm going to combine those two together, 0.2 divided by 0.1 to the power of y. Now I have 4 equals 2y. So this tells me y is second order for b. Okay, so now that I have both of my orders for A and B, I can write my complete rate law expression. So here, my rate, I'm in green. Rate law expression is rate equals K, A to the power of 1, or just leave it how it is, and then B to the power of 2. And that is my rate law expression for this reaction. Now, it does want me to solve for K now. So now that I have my exponents, I can actually choose any trial I want. So let's use trial 1. If you end up using a different trial, I will say this data that I have for this problem was actually one that was performed in the lab. So sometimes you actually might get a different K value. Don't stress out, because when you do an experiment, not every trial is going to be perfect. So the rate law constant might change. Now for the AP test or any type of released free response, they try to make sure the data is perfect. So the rate law constant is constant for every single trial. But again, not everything is perfect, and this was experimental data. So there was going to be sources of errors where a rate law constant wasn't always going to be the same. But don't stress out. So using trial 1, I'm going to plug in everything using the trial 1 data, okay? So the rate law in trial 1 was 0.18. I'm solving for K value and its units. Value of A is 0.10 to the power of 1, and then 0.20 to the power of 2. So let's put this in our calculator and solve for K. I get K as 45. Now we have to figure out the units. So our overall order is 2 plus 1, so that is 3. So here, remember, to figure out K units, we will do 3 minus 1, that's 2. So this is 1 over molarity squared. And don't just write time. Here, looking back at the top, it actually tells me it's in seconds from the rate. That the rate will tend to tell us what the actual units for T is. And so here I get 45. My advice for doing these types of problems, excuse me, is to always tell the rater or grader what trial you are using to solve for the value of K. So then they can see what values you took. Because what if, let's say, I accidentally put 0.72 and I chose the wrong one? Then they can see there was just a simple error rather than you were not even doing it correctly. Okay, so always tell them what trial you are using. All right, so I do have a you-do problem, okay? Here, determine the rate law, but I also want you to solve, it doesn't tell you to solve for K, but I do want you to solve for K just for good practice. So why don't you pause the video, try this out yourself, get the rate law expression, and then get the value of K with the correct number, units for that K value based off the overall order, okay? All right, so pause video, try this out yourself. So in this example, for the S2082-, trials 2 and 1 are what I chose. Found that X was first order. And then for the I-, trials 2 and 3 were the ones I used and got first order as well for that. So the overall rate law expression will just be taking x and y to the power of 1. So our overall order was 2, 1 plus 1. So then to solve for k using trial 1, I just plugged in all that data from the chart, and I got my k as 0.0061. And then because overall order was 2, 2 minus 1 meant that it would be molarity to the first power. And it was seconds for time. Just looking at that initial rate, it had seconds. So scrolling down, again, we had referenced this earlier, and I just wanted to reference it again. The units for K is just 1 over molarity. Now, you will also notice it kind of looks like this as well, but that's just because molarity is moles over liter because of N over V. So since molarity was on the denominator, that's why I had moles on the denominator and liters on top. So you could also write it in whatever way you'd want to as well. And knowing that N is overall order, sum of all the orders. So I have 3 examples right here. I want you to pause the video just to make sure we have the units for K down, just because they are a lot of points. Just because they tend to be 1 point, and that's just an easy point we should be able to get. So yeah, pause the video, try this out yourself. All right, so in these 3 examples, the first one, overall order was 3, so it's 1 over molarity squared times time. 2, it was 1, so 1 minus 1 means it goes away, so 1 over time. And lastly, overall order was 2, 2 minus 1, 1, 1 molarity over time.